Thank you, Tom, and thanks very much to the organizers for the very nice invitation. Okay, so today I want to start with some motivation and then introduce a class of random growth models on the complex plane, which are called Hastings-Levitov models. So motivation, we want to explain the formation of fractal-looking patterns in nature. So here are some examples. These are manganese formation on limestone, lightning, some kind of lichens, and underwater corals. So we see these kind of ramified structures, and how do they form and why. And an example which I like very much to explain the class of models which I will work on is bacterial growth in stress conditions. So here is a colony of bacteria which is trying to grow in space, and you should think that the nutrients, the resources in the surrounding environments are limited. If they weren't, you would see this kind of spherical growth. But as you start lowering the amount of nutrient present outside the colony of bacteria, this fingering structure appears. And as the level of nutrient becomes lower and lower, the fingering becomes more evident until it breaks the disk structure. So how would you go and build mathematical models for this class of phenomena? Well, you can work in a discrete setting or on the continuum. And I will start by saying something about the discrete approach, and later in the talk, I will move on to the continuous setting. So we're going to take the point of view that growth happens by aggregation of particles. And in the discrete setting, your particles live on a discrete graph that in the pictures I will show you is the d-dimensional grid, but you can consider more general graphs. And at each step, you look at the boundary, the outer boundary of your aggregate, and you prescribe a probability measure to choose the location of the next particle which aggregates to it. In the continuum setting, you have to prescribe a probability measure for the boundary of your continuum aggregate, which well, might look slightly more complicated than the discrete setting. Okay, so a first famous model, a discrete random aggregation model, is the Eden model, which was introduced to explain the growth of lichens, as in these two pictures. So these are organisms which reproduce in an asexual way on the boundary of the aggregate. And so Eden introduced what's now called the Eden model, in which he said, well, let's grow random clusters according to the uniform measure on the outer boundary of it. So you look at the outer boundary of your cluster, you pick uniformly at random one of the sites on the boundary, and you add a particle there. And that's your next cluster after one time step. And this is a picture of a large Eden cluster. This picture was made by Jason Miller in Cambridge. And the colors here represent the time of arrival of particles. And we see that the structure looks pretty regular. It doesn't really look like a disk. We can see that the growth is slightly faster in the preferential direction of the underlying grid. But it looks like the fluctuations are microscopic in the radius. And in fact, this is known to be true. So it's been known for a while that the Eden model has a limiting shape. So if A of t is the random cluster after time t, I don't want to comment on how time is indexed in this theorem, then, well, this cluster is very close to a deterministic shape, which is called A here. And one might wonder whether this shape is a disk or not, and it's known that it's not a disk if the dimension is high enough. So this was already proved in 1984 by Kesten for very, very high dimension, and it was improved to a lower dimension, but to determine whether the Eden clusters are disks or not in dimension, say, 2 or 3, it's completely open. Okay. Another famous model which falls in this class is diffusion limited aggregation. And if you think about the bacteria colony example, which I showed you at the beginning, you should think of the Eden cluster as the high nutrient regime, whereas diffusion limited aggregation is the low nutrient regime. So your bacteria colony is just a set of vertices, a connected set of vertices in ZD. You initialize it in some way, say one particle at the origin, and I'll define it recursively here. Say you already have your cluster after some number of particles arrived. How do you aggregate the next one? Well, you might think that there is just the concentration of nutrient outside your cluster, your colony of bacteria is very low. So there is basically one particle of nutrient diffusing around outside your colony of bacteria. And when it comes into contact with the boundary of your cluster, there you have a new particle arrival. And so this means you start a simple random walk very far away from the cluster, formally from infinity, and you wait for it to hit the outer boundary of the cluster, and that's the arrival location. Now, this is a simulation of a large diffusion-limited aggregation cluster. This has been obtained by Van Sambe-Farah, and you can definitely see the two preferential directions of the underlying lattice. It doesn't look like a ball. It's completely open to show that this picture is not a ball. And there are very few results on diffusion-limited aggregation. You might think that this fingering structure depends on the fact that you are on ZD, so you might try to simulate diffusion-limited aggregation off-lattice. Say you take little spheres moving around like Brownian motion, and when they come into contact, they stick together. And this is what it looks like. So still the fingering structure is there, but you don't see the two preferential directions because you are not on the lattice any longer. And just to say, simulating DLA, it's far from trivial. Just because the simple random walk takes a long time to hit the boundary of your cluster, it will do it, but it might get very far. And if it gets very far, how do you do it? Well, you have to take it back, to bring it back somehow without spoiling too much the distribution of the random walk. And I like this comment by Sander on simulating diffusion-limited aggregation. Now there are several ways of coming up with quicker simulations. Okay, almost the only result which is available on DLA it dates back to 1987. It's due to Kesten, and it's an upper bound for the speed of growth, depending on the dimension. DLA in dimension 1 is trivial, but if you are in dimension larger than or equal than 2, then what Kesten shows is that if Rn denotes the radius of the radius of the smallest ball that contains your aggregate centered at 0 after n particle arrivals, that doesn't grow it doesn't grow faster than n to the 2/3. So it's an upper bound for the speed of growth. There's no lower bound better than the trivial one available. And he has a similar estimate in higher dimension. Okay, and so these are the two models we just discussed. The model high nutrient regime, diffusion-limited aggregation, low nutrient regime, and you can think of interpolating between these two to model a sort of intermediate concentration of nutrient. And how do you interpolate? Well, there are several ways of doing it, but one is to think of DLA as growing according to harmonic measure, which is just the heating measure of a simple random walk on the boundary raised to the power 1. Either model grows according to the uniform measure, so harmonic measure to the power 0, and you can raise the harmonic measure to some fractional power gamma between 0 and 1, and that takes you from either model to DLA and back, according to the value of gamma. And this is not a simulation, this is just a picture of something which is believed to behave like dielectric breakdown. But let me advertise a very recent result by Ilya Losev and Stas Smirnov in 2023 on dielectric breakdown models. So what they can show is that there is also for dielectric breakdown models of parameter eta, so eta is what I called gamma in the previous slide, one can get an upper bound for the speed of growth, which depends on eta. And if eta equals 1, then you recover DLA. The result still applies, but doesn't give you a better exponent than Kesten. So they don't improve Kesten's result, but they do generalize it to dielectric breakdown models, which, yes.
So you can take eta bigger than 1 here.
Yeah, up to 2.
Does something interesting happen at 2?
That's a good question. Not sure.
You see that the boundary becomes linear.
Or the n.
So,
So
let's do it.
No, the end factor is power 1.
Okay, becomes linear. There is only the log n, which is non-trivial. Okay, so after Rn is the radius of the ball after n arrivals, so Rn cannot grow larger than n. So
maybe it starts to be linear.
Sorry? This is just an upper bound. Okay. So this is all I wanted to say about the discrete approach. And now let me switch to a continuous approach in which I want to define random aggregation models on the complex plane. And the definition is a bit more technical, but there will be more advantages on working with the complex plane. One is that we avoid discretization altogether. So for example, the dependence on the choice of the underlying graph is completely bypassed by working in the continuum. The other one is that by working on the complex plane, we have access to all the tools from complex analysis, all the rigidity of holomorphic maps. And this will also be good for simulations. So you will see from the definition of the model that these are easy to simulate. I'll show you pictures, which was non-trivial in the discrete setting. So in the discrete setting, Eden model, okay, it's easy to simulate. DLA, as I said, you have to be careful if your random walk goes too far away. And dielectric breakdown model, it's hard because you have to simulate according to a power of the harmonic measure on the boundary. So you have to first compute the harmonic measure on the boundary, raise it to some power, and then sample from that. Okay, so let me define the Hastings-Levitov aggregation model, and please stop me at any point if you have questions. So we want to mimic diffusion limited aggregation on the complex plane. And we have to start from some initial shape. Here I take it to be the unit ball, centered at 0. And maybe at the end of the talk, I will comment on more general initializations. And we want to aggregate particles, say, to this unit ball according to the harmonic measure. So let's take a Brownian motion starting from infinity and wait for it to hit the boundary of the ball, and we will aggregate a particle there. This is the analog of a simple random walk in the continuum setting. So by rotational invariance of Brownian motion, I can assume that it hits at angle 0 on the real line. So I've rotated things just at the beginning so that the first hitting point is 1. And we will aggregate a particle there. So what do I mean by aggregating a particle in this setting? Well, first of all, a particle, it's a compact subset of the complex plane, which in these pictures I took to be a slit, but you can do many more general things. For now, think of it as being a slit. How do you encode this particle arrival? Well, by the Riemann mapping theorem, we know that there exists a conformal map, a conformal isomorphism, mapping the outer domain of the unit disk to the outer domain of unit disk union the particle, which fixes infinity and which doesn't rotate infinity. There exists exactly one that does that, and I call that F. So if I give you an explicit set, you might be able to write down F. For example, for the slit, F is an explicit map. And so by aggregating the particle, we mean applying this F to the outer domain of the unit disk, mapping it to the outer domain of unit disk union the particle. Okay? And if you put the requirement that F fixes infinity and it doesn't rotate at infinity together, that gives you that around infinity, F of Z looks like a dilation e to the C times Z. And I want to mention it because C will play an important role in this talk. C is a measure of the size of the particle you have attached. And I want to give you a geometric interpretation for C, just to convince you that it should measure the size of the particle. So take a Brownian motion, now starting from a point Z, not from infinity. Wait for it to hit the boundary of your cluster with one particle, and compute the expectation of the logarithm of the modulus at the hitting point of the Brownian motion. So if the Brownian motion hits on the disk, this modulus will be 1, so the log is 0, and you have no contribution. And the only contribution comes from points on the particle, okay, and it's positive, so this is a positive number. And the larger the particle, for example, the longer the slit, the larger this number. And now you want to take Z to infinity, because this quantity will depend on Z, and the limit will give you C. This is very easy to see with complex analysis techniques and martingales, optional stopping theorem. So C is a measure of the size of the particle. It's a non-negative number, and the larger the particle, the larger C. And it's a nice way of measuring the size of the particle, because it's something you can read off your map F. Yeah, so it behaves much better than, for example, the Euclidean length of the slit. And just to keep in mind, if I give you a particle which is just a slit of length D, and you should think of D as being small, the particles in this talk will be small, their size will go to 0, so that we get a finite size cluster. Then as the size of the particle goes to 0, the logarithmic capacity is something like the square of the diameter of the particle. So if your particle is a small disk, it will be something like the area of the disk. Okay, this is all I need you to keep in mind about C. And now back to the definition of the model. We said this is what we mean by aggregating one particle. We mean applying a conformal map F. And let me call it F1, just to emphasize that it's the map that encodes the first arrival. Now we want to keep aggregating particles. So we release another Brownian motion from infinity to mimic DLA, independent of the previous one, and we wait for it to hit the boundary of your cluster. But now the hitting location is not uniform anymore, because my cluster is not a disk anymore. So how do you describe the hitting point? Well, one idea is to map out the particle for the time being, and so apply the inverse of this conformal map F1 to the outer domain of this cluster, which takes this particle, this slit, and it opens it up to this red arc on the boundary of the disk. And crucially, F1 inverse maps a Brownian motion to another Brownian motion by conformal invariance of Brownian motion. And so we know that the hitting location in this picture will be uniform around the disk. So we pick a uniform point and attach a particle here. What do I mean by attaching a particle here? Well, again, I mean applying a conformal map from the outer domain of the unit disk to the outer domain of my cluster with a slit at some angle chosen uniformly. And this map is random because the angle, the arrival angle is random, but it's random in a very easy way. You just take your deterministic map F1 and you conjugate it with a random rotation, which has the effect of centering the particle where you want it to be. And now you have to remember that you had already grown one particle, so you grow it back by applying F1. And you get your cluster with two particles. Now F1 will act on this slit, and it will deform it. So the second particle will not be exactly a slit in the actual cluster. And if you compose these two maps together, what you've done is simply compose F1 with F2. And now you can keep on going. You release an independent Brownian motion from infinity, and in order to describe the hitting location, map out the first two particles by applying the inverse of the map that grows them up. Choose a uniform angle independent from everything else. Attach a particle there by applying a map F3, and then grow back the first two particles. This will have the effect of growing back the first two particles exactly as they were, but the third particle will be distorted by the application of this conformal map. Okay, and so now in general, if you want to grow a cluster with n particles, you will have to compose n conformal maps, which depend on the arrival angles. And in a simple way, they're just deterministic map conjugated with random rotations. And they will also depend on the size of the particles you attach, which I haven't commented on, apart from saying that we call it logarithmic capacity. So let me do that. So how should we choose the length of the slits or the capacity of the slits in order to get a reasonable model? So let's try to keep things simple, and let's attach particles of deterministic length, or if you want, deterministic logarithmic capacity. So if you remember, when you attach a particle to the disk, and then to get it to the actual cluster, you grow back the previously arrived particles. And this has the effect of deforming the latest particle to something which is not really a slit. And you have to work out how much it gets deformed in order to understand the size on the actual cluster. And if you think of small particles, so this C is going to 0, the diameter of the particle is going to 0. Well, what's the length of this curve? You just have to integrate along this curve the distortion factor, mod phi prime. And if you use the mean value theorem, which is just heuristic, but this is roughly mod phi prime at the arrival point, so at the attachment point. And so that's how the length changes by the regrowth of the previously arrived particles. And now, since we are measuring the size according to logarithmic capacity, we square it because the capacity scales like the square of the diameter. So this is the actual size on the cluster of the nth particle. And, well, it depends on this complicated factor here. And how does this factor behave? Well, this factor is inversely proportional to the density of harmonic measure on the cluster boundary with respect to boundary length. And so that means if you attach at points which have very high harmonic measure, so where the Brownian motion is likely to hit, you will attach a small particle because this distortion factor is small. And if you attach at point which the Brownian motion is unlikely to hit, you will attach large particles because this factor is large. And so you don't really get particles of the same size in the actual cluster. So this model is not really like DLA because this distortion plays an important role. It changes the size of particles. So if you want DLA, you have to compensate for this distortion. And what Hastings and Levitov proposed is to accept that rather than attaching particles of deterministic size, we will attach particles of random size in order to compensate for the distortion. And the random size should be chosen exactly to compensate the distortion factor so that we get cancellation and particles of roughly the same size in the true cluster. So if you choose these particle sizes, then you get a good model for diffusion limited aggregation because you're growing according to harmonic measure and you're attaching particles of roughly the same size. And in general, you can partially compensate for the distortion by introducing an exponent alpha here. And what you get is that the actual size of the particle is still inversely proportional to the density of harmonic measure on the cluster boundary, but raised to some power. Okay. So we have a class of growth models in which, in order to build a cluster with n particles, we compose n random conformal maps. The randomness comes from the attachment angles, which are IID uniforms, but the particle sizes are chosen in this complicated way. And the alpha here regulates how much you're trying to compensate for the distortion intrinsic in the model. So you can try to work out the rate of growth on the boundary of these clusters, just to understand what you should expect. And this is a very heuristic computation, but let's index this boundary according to the angles on the unit disk. What's the rate of growth at the boundary point Z here, which is the image of e to the I theta under this map? Well, the rate of growth is roughly the attachment rate, the arrival rate of particles at this location, times the size of the particle that arrives at the location. And the attachment rate, well, it's the harmonic measure. So per unit length, the density of harmonic measure is, this is an easy computation using conformal invariance of Brownian motion. It's this factor here, the inverse of the modulus of the derivative of your conformal map on the boundary. And then the particle sizes is, well, if we take alpha equals 2, it's just C, some constant, that's DLA regime. But if you have a general alpha here, it will be C times this factor to the 2 minus alpha. So the 2 is the conformal distortion, and the minus alpha is the factor you introduce to compensate for it. And so if you just multiply the exponents sum up, and you get the harmonic measure at Z raised to the power alpha minus 1. So this should remind you of the discrete models I discussed at the beginning. The clusters are growing roughly according to harmonic measure on the boundary raised to some power which depends on alpha, which is this parameter which we introduced. And so you get a one-parameter family of models which, well, if the rate of growth is harmonic measure to the alpha minus 1, when alpha equals 1, the rate of growth is roughly uniform on the boundary. And so you should see something like the Eden model, a continuous version of the Eden model. When alpha equals 2, you're going to, according to harmonic measure, and you should see DLA. Between 1 and 2, you should see dielectric breakdown model with parameter alpha minus 1. But nothing prevents you from considering other values of alpha. And these are the Hastings-Levitov models. OK, so this is the definition of the models. And what do you expect? Well, when you grow according to a negative power of the harmonic measure, things should be nice. Because if you try to grow arms, regions which have high harmonic measure, their growth will be slowed down. And if you try to leave fjords, their growth will be sped up. And so you expect nicely looking clusters with deterministic shape and microscopic fluctuations. And this is a simulation of the alpha equals 0 case, in which there's no, this factor is just not there. When alpha equals 1, you should grow roughly uniformly. So that's the analog of the Eden model. And above 1, you're growing according to a positive power of the harmonic measure. That means if you start getting irregularities, you favor them. And so you don't expect deterministic looking clusters. In fact, we see this kind of randomly looking macroscopic shape, random looking macroscopic shapes. And for alpha equals 2, you should get diffusion limited aggregation. And so the regime below 1, it's, well, you expect deterministic limiting shape, and by rotational invariance, you expect disks if you start from disks. And above 1, you expect macroscopic fluctuations, and this is what Hastings and Levitov called turbulent regime. And at alpha equals 1, there should be a phase transition. OK, so this is the physics conjectured, but the difficulty in analyzing this model is the presence of this factor here, because, well, the size of the kth particle depends on what the cluster looks like after k minus 1 arrivals in a complicated way. It depends on the map phi via phi prime, which is badly behaved on the boundary, because you're looking at phi prime at the boundary of holomorphicity of this map. Now, these are all nice maps, but on the boundary, they can get really badly behaved. And also, you do this nasty operation of taking the modulus and raise it to the power alpha. So just to get started with the analysis, let's introduce a regularization parameter sigma, which says, rather than looking at this map, the derivative of this map, right on the boundary, where it could be 0, it could be infinite, we're going to move slightly away from the boundary. Well, we hope that if sigma is small, as the cluster grows, well, this regularization shouldn't really matter. It's just a way of doing mathematics on it. And if you want to visualize this regularization, it just amounts to taking a disk of radius e to the gamma, so 1 plus gamma, 1 plus sigma, slightly larger than 1. Sigma is something small. and mapping it to the actual cluster, and you're just going to pretend that the cluster is the red one rather than the black one, which is more complicated. Okay. There is, so the presence of this factor makes things very hard, except when alpha equals 0. When alpha equals 0, the factor is just not there. You're accepting the distortion in the model, and you just have a composition of IID conformal map, random conformal maps, where the randomness comes from these IID angles. So this case is by now well understood. And this is the case where you expect disks, because you are growing roughly according to harmonic measure to the -1, so the inverse power of the harmonic measure. And already in 2012, James Norris and Amanda Turner proved that this is indeed the case. So in the small particle regime, by which I mean the number of particles goes to infinity, but the size of each particle goes to 0, so that the size of the whole cluster goes to some positive number, say 1, or it's convenient to call it T for what will come later. Then in this small particle regime, your random map phi n is very close to a deterministic map, which simply grows a disk of radius e to the t around the origin.
So is this true even if you start with a different shape instead of the disk in the middle?
So the alpha equals 0 case is very easy, because so we know everything that happens if you start from a different shape, because you can just conjugate. So you map it to the disk, you grow your cluster, and then you map it back. If alpha is non-zero, it becomes very non-trivial to understand what happens, and maybe I'll say something at the end, but we don't know. Okay, and this is also true if you approach the unit disk slowly as you grow the cluster, so you don't need to stay bounded away from the cluster. And you don't need the particles to be slits. You can take any compact subsets of the complex plane that you like. It's just important that the complement of the particle union the unit disk is simply connected, because you want to be able to use the Riemann mapping theorem. Okay, and to visualize this result, I'll show you some simulation done by Henry Jackson when he was a student in Cambridge. So what Henry did is he took 20 concentric circles with radii slightly larger than 1, increasing, and he mapped them via the conformal map that encodes the cluster growth. And you can observe what happens as the cluster is growing. So the closer you are to the unit disk, the closer you get mapped to your cluster, and so you feel the boundary of your cluster. But see, you don't really go inside. You only feel the exterior boundary of your cluster. And the further you are, the more regular you are. And the theorem says if the radii of these curves are fixed, then as n goes to infinity, they will converge just to larger circles. And when I said you can let R go to 1 as the cluster grows, I mean you can shrink these red curves towards the cluster as the cluster grows, but you shouldn't do it too quickly that you can actually get in the fjords, because then you break the shape theorem, as it should be. Okay, and just to say, the internal structure of these clusters is also very interesting. I'll just mention this very quickly. You can look at, so you're growing trees, and you can look at any 2 points and trace back their ancestry lines to the unit circle. And well, if these are random lines, which if they meet, they will coalesce and stay together. And what James and Amanda proved in the same paper is that in the scaling limit, these backward coalescing random curves converge to backward coalescing Brownian motions. And for any finitely many points that you take in your cluster. And you can also do it outwards, and you get the dual of this picture, which they call the gaps, and those converge to forward coalescing Brownian motions. So the gaps are like the shortest paths that you can take to escape your cluster without touching it. Okay, just to say, also the inner structure of these clusters is interesting. And once you have a shape theorem, you can wonder, well, what happens if I zoom in and look at the fluctuations around the limiting shape? And so this is, again, for the IID case, the alpha equals 0 case, in which you just accept the conformal distortion, and so you have IID conformal maps. Then you can embed your process in continuous time, and this is why T was called T in the previous theorem. So you have arrivals at rate C, and so after, and so at time T, you had roughly T over C arrivals. And as C goes to 0, so N goes to infinity, you get a process of holomorphic functions, which you can rescale by dividing by what turns out to be the right factor is the diameter of the particles. So the square root of C is roughly the diameter of the particles. So this is the size of the fluctuations, and you get that this sequence of random functions converges to a Gaussian random map. And in fact, you can do it also as a process. So you get a process, catalog process of holomorphic functions. And in distribution, this will converge to a continuous Gaussian process in the space of holomorphic functions, which is conveniently described as a solution to a stochastic PDE. Now, so this PDE is a very nice PDE, and just to show you how nice it is, I'm going to take the function and expand it in Laurent series. It's a holomorphic function, so I can do it. And I can tell you the dynamics of the Laurent coefficients. And this will decouple, so they will evolve independently. That's just by rotational invariance. And there will be Onstein-Uhlenbeck processes with mean reverting speed depending on the Fourier frequency k. So higher Fourier frequencies relax to equilibrium faster. And the equilibrium, it's just, well, the equilibrium of the kth Laurent coefficient is a Gaussian distribution of a variance roughly 1 over k. So this should remind you, this field on the boundary should remind you of well, a log-correlated field in 2 dimensions. It's just that we're restricting it to the unit circle. And it's a close relative to the Gaussian free field. It's called augmented Gaussian free field. And the augmented accounts for this +1 here. So the Gaussian free field would be 1 over k. And the +1 here is due to the fact that the size of the boundary is increasing in time because you're growing disks of larger and larger boundary. Okay, and just to tell you how you put your hands on this is the IID case. Well, you want to quantify how your random map changes in one particle arrival. So you're going to compare your map phi n with phi n minus 1. And if you do a Taylor expansion, well, this is roughly the derivative of phi n minus 1 times the map that accounts for the latest particle arrival, which is, well, close to some explicit map that depends on the arrival angle. And so if you do a martingale decomposition for that, you find out that the drift, it's very easy to compute. It's explicit. You just have to compute this integral, which is 1. And so you put these two things together and you build a martingale. So we have martingales in the IID setting. And, well, OK, you have to control the errors in all these approximations. But this is how we put our hands on these clusters in the IID case. This is not the proof in James and Amanda's paper, nor the martingale I used in the fluctuation result. It's some better martingale that we only now have. OK, and to conclude, let me tell you, well, what happens if alpha is non-zero? Because I only discussed the IID case, and the difficult part is to control this factor here when alpha is, well, any positive number, really, there is the problem of controlling this factor. So, well, if you try to mimic this approach, you get into troubles because you don't really have martingales. You have this complicated factor here, which is the derivative of your map very close to the boundary. Sigma is some small number that you have to control. And, well, there were some results, some previous results, which said, well, if sigma is small but not too small, in fact, then this number should be close to some constant, well, which only depends on n and on alpha. And so if this number is roughly deterministic, you're back to the IID setting and you still expect disks. And this is a result that goes back to 2013. So if sigma, the regularization parameter, goes to 0 very slowly, then you converge to disks for all alpha, which is strange because alpha equals 2 is DLA, alpha, you don't expect disks for all alphas. So this tells you that the sigma is important. The speed at which sigma goes to 0 really determines what your clusters are going to look like. It's not just a regularization parameter that you can ignore. And what you would really like is for sigma to be of order square root of c, which is the diameter of your particles, which means you do see the single particles in the cluster. And so we wanted to address this with James Norris and Amanda Turner. And to start with, let me modify the model a little bit. So if you remember, I started by telling you that the growth rate is determined by the product of two things, the attachment rate and the particle sizes. And the alpha governed the particle sizes. But you can think of compensating for the conformal distortion in the model by changing the attachment rate rather than the particle size. So what you can do is you can make sure that you get the exponent you want of the harmonic measure by accepting the conformal distortion, but then changing the rate at which particles attach according to the density of harmonic measure on the cluster boundary. And so this is what the parameter eta is doing here. Eta has the same role of alpha, but now the model has changed. So particles have roughly the same size in the disk picture, so in the left picture before you map them back in the cluster. That means you accept conformal distortion. But you choose the attachment angle, the arrival angles, according to this complicated probability measure. And that should have the same effect, deterministic shape below 1 and macroscopic fluctuations above 1. But it's much easier to analyze because at least at infinity, your random maps are deterministic, and that helps a lot. And so in this case, in this regime, what we proved is the following. For any eta below 1, if you remember, 1 is where you expect the phase transition, the Eden model. So as long as you are below the critical point, and for any sigma that goes to 0 slightly faster than square root of c, so slightly faster than the diameter of the particle, which is optimal, the random map converges to a disk. And we have an explicit error bound in the small particle regime. So this is optimal because if sigma goes to 0 faster, then you expect a completely different behavior because now you start seeing the single particle's arrival and not an averaged effect from many particle arrivals. And we can also do the eta equals 1 case, which is the critical point. We just need to regularize a bit more. So sigma can go to 0, but it shouldn't do that faster than c to the 1/3. And then we have the same theorem, disk shapes. And that required identifying the effect of one particle arrival on our conformal map phi n, exactly as before. And so we were able to pull out an explicit operator apart from error terms. And the operator I wanted to show to you because it's a very nice operator. So if you expand everything in Laurent series, it's just a multiplier operator, which multiplies the kth Laurent coefficient by a number which is smaller than 1. So it makes things nicer. If eta is below 1. If eta is equal to 1, well, it's very close to being just the identity. And if eta is larger than 1, then this blows things up. And this is exactly what you expect from the heuristics that I showed you. And finally, we looked at fluctuations as well. And exactly as before, the fluctuations turned out to be over the diameter of the particles. Solution to an explicit stochastic PD, Gaussian. And you do see the parameter eta here in the mean reverting speed of this Ornstein-Uhlenbeck process. So that means you still have Ornstein-Uhlenbeck processes which approach equilibrium, but as eta goes from 0 to 1, so as you approach the critical point, you approach equilibrium slower. And at the critical point, you lose this nice factor, and the boundary fluctuation field is no longer log correlated, it's just an IID field. So we do see a phase transition in terms of the fluctuations. And in order to conclude, let me just mention that we started with a parameter alpha to compensate the conformal distortion via random particle sizes, which was what Hastings and Levitov proposed. That's this line. And we dropped it because the analysis was easier when alpha was 0 and eta was non-zero. So we tried to compensate for the conformal distortion using non-uniform attachment angles according to the harmonic measure. And so that's the line that we just discussed, where we discussed the shape theorem and fluctuations up to the critical point and including it. But you can think of working with both parameters being switched to non-zero. And it turned out that the growth rate on the boundary just depends on the sum of these two parameters. If you go back to the heuristic that I showed you, the exponents were adding up. So along these dashed lines, you expect the same behavior of these models. And in fact, this is what we showed in a second paper, which is more technical because you have these random particle sizes as well. But we could extend the shape theorem and fluctuation results also to this regime, which in particular includes the regime in which the particles have roughly the same size in the actual cluster, because alpha is equal to 2, you're exactly compensating for the conformal distortion. And you grow according to uniform measure. And so you have a continuum analog of the Eden model. So this tells us that this version of the Eden model has disk shapes, which is open and believed to be false on ZD. And well, it tells us that it has Gaussian fluctuations. That means the regularization parameter is still too large because you don't expect Gaussian fluctuations for the Eden model. And this is what the fluctuation looks like. You see the behavior just depends on the sum of the two parameters, but exactly the same, except there is a time change, which depends on alpha, which regulates the random particle sizes. And that's all I wanted to discuss. Just to tell you what happens next. Well, in the Eden case, as I said, we see Gaussian fluctuations, which tells us that the regularization parameter was too large. So sigma was going to 0 too slowly. We regularized too much. And what you expect for Eden is KPZ fluctuations. And this is work in progress with James Norris and Amanda Turner. Then another important question is what happens if you don't start from a disk? As I said, in the IID case, well, we know, and you can just conjugate with the map that takes you back to the disk. But when the parameters are non-zero, well, this conjugation just doesn't work because you have the distortion factor, which gets changed as well. And we have a guess, we have a conjecture for the for a deterministic partial differential equation that describes the growth of these shapes where you expect them to be deterministic, but we haven't proved it yet. Then another important point is what happens if you start taking into account single particles rather than an averaged effect. So sigma of the order of the diameter of the particle. And then finally, the very interesting setting, the very interesting regime is what happens when you grow according to a positive power of the harmonic measure. Because to now, we're working with negative powers or 0 power of the harmonic measure. But if you go to positive, you should see macroscopic fluctuations. And that we see that things changed because, for example, the operator P that I showed you becomes a really bad operator. But well, one would have to show that that's the leading order effect, and that's still out of reach for the moment. And thank you.